Next, we will discuss about the isolated system. That is, if there is no energy transfer between the system and its environment. It means that from the previous slide, if the system is isolated, the total transfer of the energy is zero. And when the total transfer of the energy is zero, it means that the change of the total energy of the system is zero too. We may expect that for an isolated system, the total energy is conserved. The total energy of the system is conserved. Anyway, the energy can change form, and it can transfer from one part of the system to the other part of the system, but the total energy in any form is conserved. If we are concerned only with the mechanical energy in our system, it means that the change of the mechanical energy of the system is zero in this isolated system. So, if we deal only with the mechanical system, we have that the total mechanical energy is conserved. It means that it's not changed in time. This is the concept of the conservation of energy. Conservation of energy. That is, if there is no energy exchange between the system and the environment, the total energy of the system is conserved in any form. And if we focus on the system with the mechanical energy only, the total mechanical energy of the system is conserved. The trick or the point of this issue or this problem is that what is the boundary of the system? If you define the boundary of the system in one way, you may find that the energy of the system is not conserved. But if you extend the boundary of the system to cover everything that involved with your problem, you will find that the total energy of the system is conserved. Okay, let's see a simple example. Consider the book Earth system again. Okay. First, if we define the system as the book only. Okay, so if we define this is the system, if we hold the book at the position yi at this position, and then we release the book, the book will drop down, okay, by the gravity, and the gravity will do work to the book, and the book will gain the kinetic energy. So in this situation, we have that the change of the kinetic energy is equal to the work done by the gravity, which is equal to the mgy minus mgyf, mgyi minus mgyf. Okay, this is the work done by the gravity to the book. However, from the definition of the potential energy, we have that Ug is equal to the mgy. So we can write this as delta K is equal to the minus of okay, let's go to the detail a little bit, is equal to the Ui minus Uf, which is equal to the minus of delta U, delta Ug. Okay, this is the gravitational potential. Now, if we rearrange this equation, we have that delta K plus delta Ug is equal to 0. So the total change of the kinetic energy and the potential energy is 0. Now, if we change or if we extend the boundary of the system, that is now it include both the book and the earth as a system, we can interpret this equation that the total energy of the system, is conserved. That is, if you include the kinetic energy and the potential energy, the gravitational potential energy, if you add this up to this problem, the change of the total energy is 0, and this is the conservation of energy. The conservation of energy. You can see that it depends on the boundary of the system. If you look at the book only, the energy of the book is the kinetic energy, and the total energy of the book changed by the work done by the gravity. But if you extend the boundary of the system to include the earth and the book, you can see that the total energy, which is the kinetic energy and potential energy is conserved. So, for the isolated energy, for the isolated system in this example, is the book and the earth. The total energy of the system here, we only concerned with the mechanical energy, is conserved.